In this video, we derive the small angle beam equation that explains how strains accumulate over the length of a beam to change its shape. We'll start with some definitions. So V, lowercase v, not to be confused with capital V for shear force. So lowercase v for vertical is the vertical deflection of the neutral axis that occurs when a beam deflects, and that is the deflection from its unstressed position. Don't get this confused with y, which is the distance of the point of the beam from the neutral axis. So here inside the beam, this indicates the distance y, whether you're down here or down here. But v is this distance here that's the point of deflection. And in general, the deflection depends on the position x along the beam. Note that v is not due to strain in the y direction. In fact, it's due to strain in the x direction as it stretches on one side and compresses on the other. That is, it is due to the bending moment or the curvature. Of course, and then at the tip of the beam, the deflection at the position L we may refer to as delta. So we want to derive equations for v of x, the deflection of x, from the bending moment. So in this picture, the red line is the neutral axis, and this is an exaggerated picture of the deflection of a beam. So we can also see this position along here that's the original x-axis that I've put there in pink. And so the deflection and the position x is along there. As we go along the red line, the position s tells us the position along the curvature of the beam, so not in a straight line, but along this curved line. And so v, a position x at value x and at height v, is this position here, v, or x comma v. That's the position of the neutral axis at s. And then at s plus ds, we'll move to a position x plus dx and a height v plus dv. When we do this, we change the tangent angle. So if we consider the tangent at s and the tangent at s plus x, the tangent angle then is this angle here that is the difference of this tangent to the x-axis, which would be the same as this distance here to the y-axis of the perpendicular to that. Now when we go up here, we then have theta plus delta theta is the new tangent angle at position s plus ds. That is, it's at the location theta plus d theta is the tangent angle at x plus dv and v plus, or x plus dx and v plus dv. So it's worth noting that this theta is the same as the theta for curvature. So this change in angle is the same as kappa as we move across here. That reflects the curvature, the rate of the change of the tangent angle with s. Also, note that theta here is the angle to the x-axis. So if we focus on a position here, we have this tangent of theta is dv divided by dx. That is, it's the adjacent over, or the opposite over the adjacent length. So that's this equation. And therefore, theta is the arctangent of the derivative dv dx. And so we can rewrite that then. Kappa is the derivative of d theta ds, which is equal to the derivative of the arctangent of dv dx with respect to ds. All right, that looks like a mess, but we'll break that down. So here we have again the same equation for kappa. Now we know that the derivative of an arctangent of y is 1 over 1 plus y squared. So if we apply the chain rule twice with y equals dv dx, that means, keeping in mind then the chain rule, dy ds will equal d squared dv dx squared, that is the derivative of dv dx, times the derivative of what's on the inside, dx ds. So that's the chain rule to get dy dx. Now we apply the chain rule twice to get kappa equals, here's our derivative of arctangent, here's our derivative of dv dx, and there's the derivative of the x inside with respect to s. So that's our chain rule twice, and we end up with that whole expression. Now, to further simplify this, we remember that the Pythagorean theorem, because we have dv is here and dx is there and ds is the arctangent, and keep in mind these are a little different because we have, we assume these are infinitesimally small, so these things still look like triangles, so ignore the fact that we go off the red curve. But the Pythagorean theorem tells us that ds is the square root of the sum of the square of the sides of the triangle. So we're then able to use that. We'll calculate here ds dx, and then we'll invert it to substitute it into the kappa equation. So ds dx here, we exchange what we just used with the Pythagorean theorem over dx, and then we can just bring this all into the square root. So simplify this term here is dx squared over dx squared once that's inside the square root, and this is dv squared over dx squared. And so we can then just say that's the square root of 1 plus dv dx quantity squared. Well, you notice this thing is the same as what we had up here on the numerator, on the denominator. And because we said we have to inverse this to go from ds dx to dx ds, this will also be on the denominator. So we have 1 on the denominator. This is the square root, so a half on the denominator. So that means we have this same expression here, but we have it to the negative 3/2. The denominator, so the negative, and we calculated 1.5. So kappa is all of that, which got rid of the terms over here and the term here, and so we just have left to multiply that by d squared v dx squared. And so this is then our new beam equation in its complete form, all in terms of simply derivatives of the deflection, or not quite the beam equation, it's the equation for kappa. So our next step is to relate this to m of x. So we had just calculated this expression for kappa. We have this Mike equation that relates the curvature to the bending moment. So if we divide both sides by IE, we get the bending moment divided by the flexural rigidity IE is this equation that we had for kappa. And so if we rearrange this to get a second order ordinary differential equation by bringing the second derivative to the left side and leaving everything else on the other side, we have the second derivative, that is the curvature of the rate at which the deflection changes with respect to distance along the beam, is the bending moment divided by the flexural rigidity times this expression of the slope of the beam at each position. So that's a complicated nonlinear equation to solve, but if we assume small angle, if we assume we have very little, we never get a large angle here, then we know that the slope dv dx is much less than 1. So for a small angle, we are looking at something like this. So this slope here is always very close to 0, certainly much less than a slope of 1. And so we can, when we take 1 plus this thing, and on top of that we square it, which makes it even smaller, this is all approximately 1. So that then allows us to write the small angle beam equation simply as the second derivative of the deflection is equal to the bending moment divided by the flexural rigidity. And this is a differential equation we can simply solve by integration if we have an expression for m of x. And so we will apply this in the future examples.